So welcome. I'm going to set a clock for, we've been at it for half an hour, so I'm going to set a clock for about, I don't know, 40 minutes or so. Maybe I'm going to try and give you guys a break at some point. So we'll do 30 minutes and we'll see where we are. So cancel. Okay, so we're in the second part of this second chapter. So it's part 2 of the one-dimensional motion. And what we're going to talk about? Well, we're going to realize that there's a family of graphs that go together if the acceleration is constant. They must have a very specific relationship in shapes. Not just any old graphs go together. And then from one of these graphs, actually, we can derive basically 4 equations of motion, which are amazing, really. And then what we can do is we can do the same thing with calculus, but then we can use these family of equations to solve one-dimensional problems with constant acceleration. And then we can solve one-dimensional free fall problems. And free fall is anything which only has the pull of gravity on it. So not when you stood on the diving board, because the diving board's pushing up, but the instant you leave the diving board, there's only gravity pulling on you. And then the instant before you touch the water, there's only gravity pulling on you. So not when you're on the diving board and not once you've touched the water, but in between, whether you're going up at the top or coming down, you're in a thing called free fall. And we'll talk about that. So constant acceleration. So if I take a constant acceleration, this is a positive acceleration, and I'm assuming that's 0, so this is +5 or +10 or whatever. Then positive accelerations will give me a positively sloped linear velocity time graph, because every second I add on the same amount of additional velocity. That's what acceleration is. Meters per second every second. It's how much velocity you add on every second. Positive accelerations, you add on a positive. Negative accelerations, you add on a negative. So the way I'm drawing it like not a very good diagram actually. If that is 0, I could also have a velocity that starts off negative and also has the same slope. The slope is caused by that. Where it starts depends upon other things in my journey, you know. So the slope is related to the acceleration. But I could also have a negative acceleration. And for this initial journey, that would simply be a downward slope. If I had that, I would expect that. If I had that, I would expect that. If I had that, I would expect that, and if I had that, I would expect that, because as my acceleration is positive and increasing, I'm adding on more and more velocity each second. And the same goes for if I was more and more negative. If I had one down here, I would be down there. All the time, I'm assuming I'm starting with this velocity at time, whatever I'm starting at time, but no law says it has to be that. All of this could have been at a different starting velocity. I just shift the thing. Now I've got to clean up a little bit because otherwise it'll be... Now, for any given velocity versus time graph, if I want to know how my displacement is going, well, I'm adding on a little bit of displacement during the first second. So whatever my coordinate was, it's a little bit more now. And I'm adding on not an equal amount, but more displacement during this second. So it's not linearly twice as much, it's more than twice as much. And now I'm adding on even more during this third session, so it's even more of a change, and so on. So this curves upwards. And of course, if this was a negative slope, it would curve downwards. And, but you get the pattern. The pattern is these three guys go together. And the ones I showed before, the only reason I picked them like that was because I wanted three graphs to talk about. So I picked three linear graphs. They weren't a family of graphs. They were just three graphs. So let's go through this. Which of these graphs are produced in a constant acceleration journey? Is this constant acceleration? Absolutely not. Yeah, that's constant acceleration, or that's constant acceleration, or that's constant acceleration, or that's constant acceleration. But that's not. That's by definition not constant. Is this a velocity time graph that goes with a constant acceleration journey? No, it's curved. You can have any kind of straight line you want, but it's got to be a straight line, because that's constant acceleration, so that's no good. What about this displacement versus time? All graphs tend to look the same. All curvy graphs tend to look the same, which is why we don't like them in labs. But yeah, I'm going to say that's parabolic. That's fine. Constant acceleration? Yes. Yeah. Constant velocity? Constant acceleration? Yes. You can tell me about the sign of the acceleration. It's negative acceleration because it's negative slope. And then constant acceleration? Yes, not because it goes through the zero. That's irrelevant. You can start anywhere you like, but it's got to be that shape. Yeah. Or the inverse. It's got to, that would be okay. That would be okay. That would be okay. But it's got to be a parabolic shape. Okay. We're going to take some math. We're going to take a graph and we're going to do math on it. And so we're going to take the velocity versus time graph, because that can go one way and it's talking about displacement, and the other way it's talking about acceleration. So it's kind of nice. I'm sorry, you take the slope and you're talking about acceleration, you take the area under the curve and you're talking about displacement. So the first thing I do is I say, well, this is a straight line, so y must equal mx plus b. And the y, well, it's the answer I get at a given, I'm going to say time interval, because I'm starting off at 0 here, so the time interval is t seconds, but I won't always start off at 0. So let's be safe and call this the time interval delta t. Well, this is my value of y, which is v final, and my slope is my acceleration, and my x is my displacement, my amount of time. Displacement meaning it's the time interval, my duration. And my y-axis intercept is vi. So I got Vf equals Vi plus At, and that's like a very famous kinematic equation. Well, that was kind of cool. Let's now think about areas under the curve. This is a trapezoid. In England we say trapezium, but trapezoid. This is a trapezoid. And the way you get the area is you go the left-hand height plus the right-hand height divided by 2. It's the average of the heights multiplied by the width. And for those of you who are kind of like, you like the math, what I basically do is I cut that little corner off and I find it fits nicely into there. So I end up with a rectangle. The rectangle is the base times the average height, and there's the average height, and there's the base. So it's not a magic formula. It's just, the logic that comes out of a way of seeing it. Okay. It's a half times the left-hand height, which is Vi, and the right-hand height, which is Vf, times the width, which is delta t. Again, I'm going to use delta t rather than just t because it's the duration. And so I have my second equation of motion. Man, I wish I'd been around 400 years ago, because I'd be famous by now. This is not hard, and yet, 400 years later, we're still using these equations. trapezoid is basically just a rectangle with a triangle. It's nothing fancy. It's just a fancy name for a shape. So let's just treat it as a rectangle and a triangle. So the area is the base times the height for the rectangle and a half the base times the height for the triangle. I'm sorry, I put multiplies in because that's the way I was taught to do. Multiplies an x, and of course in algebra you realize you can't do that anymore because, you know. So I should have put parentheses around it, but you know, whatever. And for this rectangle, it's going to be vi times delta t again, delta t. So there's my rectangle. And then for my triangle, it's just half the base times the height, and the base is delta t, and the height, well, it's vf minus vi. So this is the triangle, piece of cake. Now, that's correct. And all I'm going to tell you is that textbooks are a product of good science that's been massaged and manipulated by teachers to be a bit more insightful. I'm sure the people doing good science would be really upset about that. But what I want to get across to you is the fact that it's not that if you had stopped at this box here, you would have the wrong answer. It would be a perfectly right answer, but it wouldn't be as useful an answer as we can get with a little bit of insight. And the insight is, if I look down here, that Vf minus Vi is equal to A delta T. And so rather than having that Vf minus Vi, I say A delta T. And so I get delta x equals Vi delta T plus 1/2 A delta T squared. Another correct equation. The difference is this is going to be more useful. And I'll explain why in a minute. And then the next thing we do, and this is, I don't know, it's just me, I look at this and I go, oh man. So Vf equals Vi plus A delta T, and Vf squared equals Vi plus A delta T squared. So Vf squared equals Vi squared plus 2 Vi A delta T plus A delta T squared. So Vf squared equals Vi squared plus 2A Vi plus delta T plus 1/2 A delta T squared. So Vf squared equals Vi squared plus 2A delta X. And it just doesn't speak to me. I don't know. It's just my prejudice. I love diagrams. That kind of goes, oh, it's just a whole bunch of algebra. And that's shame on me. I mean, I should try and love that a bit more because it's incredibly useful. It just gave me another answer. And so I have Vf equals Vi plus A delta T. Now, let's get some. Why are these 4 useful equations, and why did I mess around with this third equation? What parameters is this all about? It's not about temperature, and it's not about density. What is all this about? Give me the parameters. What are the variables? So delta T,
initial velocity, final velocity,
Vi, Vf,
position or
displacement, and
acceleration.
Now, so try and be firm with yourself. It's delta T. It's a change in time. Try and be strict about when is it a time and when is it a change in time. I know I wasn't because I put that T down there, but you know, try and be strict about that. And try and be strict about positions versus displacement because they're not the same thing. They're both differences versus an absolute value. I got 5 variables. How many variables are there in this? What's missing? How many variables in this?
Missing acceleration.
4. Acceleration mission. How many's in this?
Missing final velocity.
There's 4, and final velocity is missing. How many in this?
Missing final time.
There's 4,
Change time.
and duration, changing times there. So we have 4 equations, and one of them is missing a different thing each time. It's very useful. That's why we changed this third one, because it was in Vi delta T, Vf, Vi delta T. So it was doing the same letters as this guy over here. So it wasn't adding anything, whereas now it's adding something. So it's kind of it's really useful, really nice. We can do the same thing, of course, with calculus. Acceleration equals dv by dt, v equals the integral of a to the x dt, and just go through it. We've done it. I'm not going to spend time on it. You need to know those 4 equations. You need to know them. You need to know them as soon as possible. The sooner you learn them, the more ingrained they'll be by the test, and the less likely you are when you're under pressure to kind of get them messed up. If you write them down every time, if you write the right equation down every time you do an equation, every time you do a question, it'll help. But you need to do them. So my advice is you write them down an awful lot now, and then as time passes, you quickly get to the stage where you're kind of like, because it's not about the equation once we get going, you know. So this is how we do these problems. At t equals 2 seconds, a blue sports car. So there's my sports car. And the clock is saying 2 seconds. And it's at rest. So I'm going to say VI equals 0 meters per second. At t equals 6 seconds, so here's my sports car, and this is 6 seconds. The blue sports car has a velocity of, V final is equal to minus 12 meters per second. I got a problem with this thing, so I'm gonna say